Hey, y'all. Happy Wednesday. All right, second to last lecture is happening right now. Second to last. We're almost there. We can do it. We can do it. On the board, I've got what we finished with on Monday, looking at constructing the molecular orbital diagram for CH4. We looked at carbon, said it should be sp3 hybridized because it has 4 electron domains. We looked at hydrogen, said it's just 1s, so no big deal. We picked an energy for carbon and said carbon is here. We then said based on electronegativity and then based on energy level, how should 1s compare to carbon? Since it's the 1s of hydrogen, we were like, well, they're about the same electronegativity, so that would keep us at about the same, but 1s is lower energy than 2, so we went a little bit lower. And that was the reasoning behind that. Then we did two things, right? So we ordered it, carbon on the left, hydrogen on the right, molecule in the middle, and then we mixed. We mixed to get the number of molecular orbitals that corresponded with our new electron domains. Yeah? So we had to make 4 new things. So these 4 new things arose by combining all of these. All right, we took all 4 carbon sp3 hybridized orbitals and all 4 hydrogen 1s orbitals. Or you can think about it, I took one of the carbon sp3s, one of the hydrogen 1s's, mixed them to get a sigma CH. What does the sigma CH look like? Like this. Looks like that. So I took this picture, and I took that picture, and I drew them next to each other. That is the level of understanding that I need you to get out of this. Like literally, that's what I need you to be able to do. Are y'all okay with that? You're not, you don't want to accept it? Okay. Damn it. I want you to be able to accept that. It would make all of our days better. All right, so this is constructive interference. Right, that constructive interference gave us this sigma bonding type orbital. It's sigma because the new orbital overlap here, this new orbital overlap, is between the 2 atoms. It's along the internuclear axis. Right, so it's a sigma style thing. Another way you could have drawn this, if you're into using up more pen or more chalk. C, H. Could have drawn it like that. They are the same. Those are the exact same thing as each other. They have the same meaning. Because remember, that phase doesn't have a physical representation. The only reason the phase matters is when we look at how it interacts with other waves. Right? So the phase of our orbitals, as long as they are the same, they will constructively interfere. We get more orbital overlap there. Right? So this is why we have a bonding style interaction, because those phases matched. All right, so destructive interference. All right, because we can't only make this possibility, we also have to make the worst possibility. A higher energy possibility. And I guess that's another thing to sort of bring up. A lot of people struggle with, like, do they have to be there, though? Do they? Yeah, they do. And then, like, how do you know they're there? Spectroscopy. Like, we know they're there. So if you think about the hydrogen atom, right? We know that the hydrogen atom has its 1 electron in that 1s orbital, and we're cool with it. But you also know that you can shine light at a hydrogen atom, and that electron can go from 1s to somewhere else. Right? So until that electron goes to that somewhere else, we don't actually know what that orbital looks like. Right? We know they are there because the hydrogen's taking in very quantized bits of energy. So we know it's doing something. And then we look at it and be like, oh, that's what it's doing. Cool. That's what 2p looks like in the hydrogen atom. Like, oh, hey, that's a 7f orbital. Weird. Right? It's like the orbitals have the possibility of existing, but they don't actually look like anything until you put an electron in them. All right, so these exist, but there's nothing in it, so don't worry about it. All right, so we do destructive interference. And we get the sigma star CH. So you got 2 ways that you can draw this. We could do that, where we now have a node along that internuclear axis. If there's a new node along that internuclear axis, it is anti-bonding. That's why we get that star. Or, right, so this is totally one way to draw it. Or, we can do this. They are the same as each other. Both of them are fine. Both of them show the exact same information. And like, to be real, I kind of like the second one because I had to color in less stuff. But they're equally valid. All right, questions, thoughts, concerns about how we got to these pictures, or what those pictures mean? Yeah? The shading is not the same as where it's supposed to overlap? Yes. As you bring the two waves together, like as they physically get closer, if the phasing is opposite, right? So like if up is coming into a down, then you just flatten it out. And so this node is that flattening out. Yeah?
If I pick one shading scheme for constructive interference, does that imply a choice for the next shading?
No, you can flip your choices whenever you'd like, as long as the thing that you draw indicates anti-bonding or bonding appropriately. So like if you started here, and then you're like, you know what I'm going to do? I'm going to do that this time. Totally fine. It means you use the negative carbon instead of the negative hydrogen. Yeah? Yeah, let's get into it. Cool. How many total electrons did we have in this molecule? Valence electrons. How many valence electrons in CH4? 4 from carbon, 4 from hydrogen, that's 8 total. So we add our 8 electrons, we add them low to high, spread them out before we pair them. 1, 2, 3, 4, 5, 6, 7, 8. Cool. So now we have our electrons in the molecule. You then look at your MO diagram. You look at it. You're like, okay, I see you. I see you, diagram. I got this. It looks like Italy. Thanks, bro. Oh, sidetracked hard. Let me get back to it. Right, we have 4 sigma CH bonds, which we knew was going to happen. That's how we drew it. So the way we drew it impacted the way that we came up with this particular MO diagram. Right? And so then you're asking about like these frontier molecular orbitals. What are they? All right? We have 2 frontier molecular orbitals. We have the highest occupied, so of all of the MOs, which electrons are in the highest energy, and then we have the lowest unoccupied of all the MOs, which one is the lowest energy without electrons in it. In this particular case, it's fairly straightforward. Right, Mian? This is our highest occupied molecular orbital. Right, because that is the of orbitals with electrons, that's the highest energy, highest occupied. Then we go up top. We're like, cool, that must be my lowest unoccupied molecular orbital. Of all of the empty orbitals, that one is the lowest in energy. Okay. So let me throw a question at you all to try and give you a way to figure out why this is important. How would we use light to determine the bond strength, the CH bond strength, in CH4? How do you use light to figure that out? Take a minute, bounce some ideas off each other, see what you come up with. All right. Who's got thoughts? Any volunteers? Yeah, what's up?
Hit it with like light and then see what kind of spectroscopy wavelengths are like absorbed or emitted off of it, and that maybe that'll correspond to a different type of bond.
Okay. My favorite is that you're like, okay, we're going to hit it with light. It's like, yes, we are going to hit it with light. And then try and see what light is absorbed and observe what happens after. Yeah. All right. Looking at this, what would correspond with a bond energy? Like, how did we describe bond strength back in the day? How much energy it takes to break a bond. Right? We had your graph did this. Yeah, you with me? Did one of these. And our, right? Bond is down here. We then separate it. They're infinitely far apart. How much energy did it take to separate them? Yeah, how much energy did it take to break a bond? How do we correspond this picture to breaking a bond? Okay. How many of y'all have done discussion number 37? Okay. What's bond order? Bond order. Word. It's the thing minus the other thing divided by 2. Nailed it. All right, so unit 1, we talked about bond order being the number of lines you drew between a couple of atoms. Right? So like, that's how we started with it, like, hey, how many bonds are there? We then did resonance to say, on average, what's the real bond order? There's another way to calculate bond order, and that's using these MO diagrams. So the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals for 2 given atoms, like for 2 atoms, right? You can't have a bond order for a molecule. It's not a thing. Bond order is between 2 atoms. So if we then focus and say, okay, so if this, right, those are the 2 orbitals between 1 carbon and 1 hydrogen, right? We're focusing now. Yeah? Right now, what is the bond order for that bond? 1. How do we break that bond? What wavelength of light are you going to absorb? The one that corresponds to that energy gap. Right, so the energy gap between bonding and anti-bonding is the bond strength for that given bond. Badass. All right, so how do we use light? We're going to excite an electron from sigma to sigma star and see if an H atom flies away. Because that's what you were saying, right? See what it absorbs, then observe what it does with that absorbed light. So we're going to keep giving it light until we observe hydrogen atoms flying away. Right? Because at that point we know we've broken the carbon-hydrogen bond. Right? And the bond energy is defined as the energy it takes to break that bond. So that's really cool. The reason this is like a badass technique is it gives you that picture. Right? At a glance you can say, you know what, this should be stronger or weaker than that other one. Just comparing a few like premises of how we set the whole thing up. Yeah. So like again, everyone's like, why are we doing this? It's to help us really either predict or from that data build one of these diagrams. It's awesome. Right? Or we can build this diagram and then from the data give it actual Y values. Yeah, right now we're just sort of guessing, but we can put an energy in there after the fact, which is cool. And we can then compare that to the energy of these things, right? And we can get these energies, the atomic energies, from ionization values. Right? So we can draw this very loose picture quickly. Believe it or not, it does get pretty fast. And then apply actual quantitative values to it later with experiments. It's pretty cool. It's really powerful. Yeah.
Why don't we have to excite 2 electrons to like have the bond go away?
Got it. Why do we only have to do 1 instead of 2? Nice. So the bond order calculation is number of electrons in the bonding orbitals minus number of electrons in the anti-bonding. So we would go 1 and 1 gets us to 0. I mean, if we did both, same thing. It's just that is twice as much as we would need to do. Okay. Concerns about this particular picture? Other things you want to talk about? All right. Let's get to some slightly more complicated compounds. Not too much more complicated, but still the concept is pretty fun. For those of y'all using paper, or if you have the chance, I would say try and do landscape for this board. It's going to get fairly crowded. So if you can landscape it, go for it. If not, it'll just look cramped like it is on the board. All right, so we're going to look at our atoms with different energies. Okay. We're going to look at lithium hydride versus hydrogen fluoride. All right, so the two compounds that we're comparing are here and here. What we're going to do is construct the MO diagram for both on the exact same energy scale to try and give us an idea of like how do we deal with that energy scale. All right. So step one is always draw the molecule. Took care of that for you. Step two, how many valence electrons do each of the molecules have? So lithium hydride, how many valence electrons do we have here? Just yell it at me. 2. All right, what about HF? How many valence electrons? 8. 7 from hydrogen, 7 from fluorine, 1 from hydrogen gives us 8 total electrons to use later. All right, then we go through and say, based on these pictures I've drawn, what are the shapes? Do I have to hybridize anything? Lithium hydride, do I have to hybridize either? Nope. Lithium only has that one electron domain. Hydrogen only has the one electron domain. We don't have to hybridize. What about HF? Does H need to be hybridized? No, it just has that one domain. What about fluorine? Yeah, it has 4 domains now. It has hydrogen and then 3 lone pairs. So that's 4 things. It's going to be tetrahedral. So this is going to be sp3. All right. So step 4, we have our atoms on the outside, molecules on the inside. Then step 4b, we start organizing our energies. So the thing that we know for sure is that hydrogen is going to be the exact same energy as hydrogen no matter what we do. So let's start there. All right. So we know for sure that's where the 1s is because we picked. Lithium. Lithium 2s. Is that going to be higher in energy or lower in energy than hydrogen 1s? And how do you know? Okay, why? Orbital size. I dig it. Sure. We got all kinds of things. People just throwing correctness at me over and over again. I love it. The thing that we should start with is electronegativity. Right? Electronegativity is the big determinant in where the energy levels are compared to each other. If I look at lithium, I don't actually know how its electronegativity compares to hydrogen. I don't have that value on hand. But we can go back to Unit 1 and be like, where did electronegativity come from? It came from Z effective and orbital size. Hydrogen and lithium have the exact same Z effective. Right? They're both +1. Lithium has a larger orbital size, so the electron is held less tightly. So being held less tightly does what to the energy? Up. Right? So here we have 2s. Higher in energy because it's held less tightly. Energy lithium 2s greater than energy hydrogen 1s because the electrons are held less tightly in the bigger orbital. Solid. Right, held less tightly is easier to get rid of, higher in energy. Sweet. All right, what about fluorine? Where's fluorine with respect to lithium? Lower for sure, right? So many things are pointing us towards that. Lithium and fluorine are in the same row of the periodic table, right? Same row, so they're going to have the general same orbital size, but fluorine has a much higher Z effective. Yeah, so it's going to hold them much more tightly. So we know for sure that fluorine is going to be lower than lithium based on our Unit 1 understanding of Z effective and orbital size. But now, remembering that we're just going to use electronegativity as the combination of orbital size and Z effective, how should fluorine compare to hydrogen? Still lower, right? So we know that the electronegativity of fluorine is greater than the electronegativity of hydrogen. Therefore, the energy of fluorine is going to be lower than the energy of hydrogen. For the exact same reasons that we talked about for lithium. Coulomb's law, the more attracted, the lower the energy. Yeah? That has always been true all semester, still true. Okay, so fluorine is going to be lower in energy than hydrogen. Let's just put it here. And there's our 4 sp3 hybridized orbitals. All right, now we can say, what do they look like? What do each of these atomic orbitals look like, so that when we bring them together to make a molecular orbital, what does the new molecular orbital look like? All right, there's our lithium, there's our hydrogen. This is 2s sphere, hydrogen 1s sphere, fluorine, sp3, little lobe, big lobe pointing in the direction of that electron domain. All right, so what I want y'all to do is construct that MO, do the mixing. Mix constructively, mix destructively for both of those molecules. Get me the middle part of that MO diagram. Get me that middle part. And remember, treat it like art. Just put these two next to each other. Just draw those pictures literally closer together, and you will have done your job. All right, have at it. All right, y'all. For lithium hydrogen, lithium hydride, how many new MOs do we need to have? So how many new MOs do we need for lithium hydride? 2. We started with 2 atomic orbitals, therefore we need 2 molecular orbitals. So we're going to go ahead and constructively interfere them. Going to do a little bit of this, a little bit of that. So when I do this boxing, the reason I'm doing that box is to make sure that I remembered to use that atomic orbital, right? I could count, like I need to have 2 at the end. I do this just to make sure that I'm covering all my bases. So we go here. Here's my sigma between lithium and hydrogen. It's going to look like that. Because I physically drew them closer together. Let it be art. All right, so there's our constructive interference. We then do our destructive interference. It's going to be a sigma star lithium hydride. They're going to be just as close as they were before, but now there's a node. And that whole thing is your lithium hydride sigma star orbital. Okay, then we go to HF. How many new electron domains are there between hydrogen and fluorine? There's only 1. Right? So we can only mix to make 1 new bonding type interaction. So we're going to take some of this, some of that, constructively interfere to make our sigma HF. Which is going to look like that. There's your sigma HF. Then you're going to destructively interfere. You're going to get your sigma star HF. All right. So there's my H, there's my F. Let's do that. Which is the same as that. They're the same. Those are the exact same. No different at all. Trying to help you remember why that might be true. Oh, waves. One sec. So wave, up and down, yeah? So if here's my reference line, I went up and then I went down. That wave is going to continue. So if I go over just a little bit, the wave now looks like down then up. It's the same wave. I'm just changing my reference line, right? Like what part of the wave am I looking at? Right? Same exact wave, whether it's positive or negative doesn't change the waviness of it. Yeah? So again, those are always going to be the same as each other. It is arbitrary. That's why it's arbitrary. We get to pick the reference line. Okay, you had a thought. Yeah. Oh, like why did we only use one of the F's? Because we can only overlap one, like we can only make one new overlap. Right, because then where are all of these other ones pointing? Right, so they're in all 4 of those tetrahedral directions. So we picked the one that was pointing in the direction that made the bond to H. And so only one of those is making bonds. That's the only one we mix. Yeah.
In the top drawing, you have the 2 orbitals that they have, like it's the same size, but in the bottom one, like the non-shaded one in this case, happen to be like way larger.
Uh-huh. So I made the one in between H and F a lot smaller to emphasize that we're having destructive interference. It's like we are very much canceling out that orbital in between. And so the one on the outside is actually about the same size as it is down here. It's like this size is about the same as that size. But what we're doing is decreasing the big one. Yeah. That's a really good question. I love it. All right. So how do we deal with then, now that we know our original atomic orbitals, how much lower is that new molecular orbital compared to how much lower is this one over here? So like, how does sigma lithium hydrogen compare to sigma hydrogen fluorine? That's really tough to tell. That one's actually tough to predict, so we would need data for that. The rule that we tend to use, and this is something I'll go over Friday, but the lower energy that you start at, the lower then it will go, just to give you sort of a way to guess how all those are going to line up. So I would say for sure sigma HF is going to be lower than sigma lithium hydrogen. It's tougher to say than, like, what about the sigma stars? Again, I normally say whatever your lowest sigma is then going to have the highest sigma star. And we'll hit that on Friday for sure. Yeah. Yeah, we didn't finish it. Yeah, right, we only have 2 over here. What about all 3 of these? They don't disappear. Right, so they're still part of that molecule. You look at HF, and you're like, oh, hey, fluorine does have those 4 domains. Oh, no. 4 domains. 1, 2, 3 more are right here. Right, and these aren't mixed with anything. So they're fluorine-centric, therefore they're called non-bonding. Non-bonding, which we are forever going to call NB, fluorine, sp3. And then what does that look like? They just look like that. They just look like the same thing, and they're going to be the exact same energy level because we didn't touch them. All right, then from here, we say, great, I've mixed everything I needed to mix. Now, what electrons do I have? Yeah? So lithium hydride, we had 2 electrons. We always fill low to high, 2. We then look at HF. We had 8 electrons, low to high, spread before we pair. 1, 2, 3, 4, 5, 6, 7, 8. Right, and so one of the things that you can usually be sure of, if you drew a reasonable Lewis structure and you fill in your diagram and you've got a whole bunch of stuff in the sigma stars, you missed something. Right? A reasonable structure is not going to have anything in the sigma stars. It's just not. However, I can still make you put stuff in there by, say, adding energy or adding a charge, but most of the things we draw are fairly straightforward. Okay, so from here, you can then assign your frontier molecular orbitals. Yeah, frontier molecular orbital for lithium hydride is going to be high OC MO, and then low unoc MO. Over here, our lowest unoccupied is just our sigma star HF, low unoc MO. And then what is our highest occupied for HF? Highest occupied. Right? Of all of the occupied ones, which is highest, it's going to be your non-bonding. Right, so it's at the frontier of reactivity. Of all of the electrons that we could use, those are the most energetic, so those are the ones that we're going to use. Okay. So I've got some more thoughts for y'all. If you look at these 2 molecules and you think, like, all right, so we were talking about electronegativity, then why dipoles? Why are dipoles a thing? Right? From Unit 1, we would just use electronegativity. All right, so we had lithium hydride and hydrogen fluoride. If you drew the dipoles, they look like that. We know for sure hydrogen is less electronegative than fluorine. I'm telling you that lithium is less electronegative than hydrogen. So there's our dipoles. We can predict that. And our new info, right, a molecular orbital will most resemble the atomic orbital it is closest in energy to. Right, so think about it in terms of contribution, right? So this low energy sigma HF is being contributed to much more by fluorine than it is hydrogen, right? Energetic similarity gives you more contribution. And what that does is gives us like a fairly skewed looking molecular orbital. Right, so for lithium hydride, here's our ideal sigma lithium H. And just a delightful oval around both. The real thing for sigma lithium H is more like a squash, right? Like there's a lot more electron density on hydrogen because in lithium hydride, that H1s is closer in energy to that particular MO. It contributes more, so we see more of that orbital there. And then for HF, it'll look kind of like that, your ideal. The real thing is real awkward. Kind of like a rocket. Right? There's a lot more electron density on fluorine than there is on H. And then if you think about, hey, dipole, that just means I have stronger electronegativity or stronger electron density on the more electronegative atom. That comes from MOs, y'all. That's cool. It's so cool. Right? It's like that thing that we just say, just deal with it, right? Know the electronegativities and then draw your dipoles and then like everything will be fine after that. Which is fun. Like it works. It totally works. The reason it's working is because of this new info. Right? The MO, the way the molecular orbitals are formed, indicates our observation of dipoles. F yeah. It's so amazing. Y'all are so unimpressed. Just give it, okay. Whatever. I'm impressed. I love it. Let's keep going, shallst we? Shallst. It's not a word at all. I'm using it. It's happening. All right. So what we're going to do. Yeah, what's up?
Like going back to the second slide.
Uh-oh.
Figuring out where to put fluorine, did you consider that like fluorine has like p orbitals as well? But then will you like have like a higher electronegativity?
Yeah, so for fluorine, we just said fluorine is more electronegative than hydrogen, therefore it goes here. Got it. So the overall energy of the atom is unaffected by the hybridization, right? So like the average fluorine energy is here. And then as long as like sp3 are all the same, so we just kind of kept it there. If it were unhybridized, right, it would be like that. But still everything fluorine would be lower than everything hydrogen. Okay. I don't want that. That can stay. All right, so let's go ahead and construct the MO for N2. All right, and again, we're doing this our way, not the correct way. Which feels bad, but I love it anyway. All right, 1, you're going to draw that picture. 2, you're going to count those electrons. 3, you're going to check hybridization. So for each nitrogen, how many electron domains are there? Right, if you look at the left nitrogen, how many domains does it have? 2. Thing on the left, thing on the right. So your nitrogen is going to be sp hybridized. All right, then we do step 4. So we're going to have a nitrogen that's sp hybridized, and we're going to have our N2, and we're going to have our N, that's also sp hybridized. And then for B, we're going to get our energies figured out. Luckily, they're both nitrogen. We don't have to worry about anything. So we're going to have N, sp, P, sp. Oh, gracious me. That's just actively wrong. Fixed it. There we go. All right. Before we go any further, I want you to actually draw what each of those atomic orbitals looks like. Like, give me the actual picture. Where are the things pointing? All right? So I've got, here's my nitrogen, here's my nitrogen, here's my nitrogen, here's my nitrogen. Yeah? You have an sp orbital pointing left, you have an sp orbital pointing right. Here's my nitrogen, here's my nitrogen, here's my nitrogen, here's my nitrogen. I have an sp orbital pointing left, I have an sp orbital pointing right. Yeah, so when we hybridize, that's the reason. We have them pointing in opposite directions. Yeah?
So how do you choose the direction they're pointing? Like,
Doesn't matter.
as long as they're opposite each other, like it could be like north and south? Or...
Exactly. Like it could be north-south, it could be in-out. In this particular case, I'm basing it off of this picture.
Okay.
Yeah. So like I drew the picture in the x-axis, so that's the one that I'm going to use. Yeah. The nitrogen. So if you go back to Mondays, like the hybrid is, when N is hybridized as sp, or when anything is hybridized as sp, it still needs its 4 atomic orbitals. So you hybridize the s and the p, and you're left over with the other 2 p orbitals. All right, and so the ones that we left over, so this is using px. So we have py, t, and we have pz. So we have all 4 of those atomic orbitals, and now I'm giving them actual shapes and actual directions. And so what I want you to do, now that you have those actual shapes and actual directions, is correctly combine them to make N2. And so take a couple minutes, try and figure out which of these orbitals do you have to combine to make the observed N2. Have at it. I cheated. Okay, why did I bring those 2 together? Why were those the 2 I picked? Because, yeah, when you bring them together, they increase overlap between the 2 atoms. Right? So when I physically draw these next to each other, they overlap a whole hell of a lot between the 2 atoms. Right? We increased electron density between the internuclear axis. That's giving us that sigma bonding type orbital. Right? What I want you all to be able to do is for all of these, do the sigma star pictures on your own. So every triple bond is a sigma and then 2 pi's. So are we going to use the sp orbital to make a pi bond? No. We can't, right? Pi bond is above and below the internuclear axis. There is no new density along the internuclear axis, so we're stuck with using the p orbitals. Right, so our p orbitals have to overlap to give us the pi bonds. All right, so we're going to overlap py and pz. I'm going to get 2 of these, pi and n. My dotted lines, again, are just saying I'm using these, I'm keeping track, they're ending up here. All right, they're then going to go up in energy to get pi star. All right, then what do those pi bonds look like? Right, you're going to have 2 of them. You're going to have 2 of them. So you can have that. And gracious. Some of that. Those are your 2 pi bonds. One in the y-axis, one in the z-axis. Right, that gives us 6 new molecular orbitals, but we need more than that. We started with 8. So the other 2 are your leftover sp hybridized orbitals on nitrogen. Non-bonding nitrogen sp. This one is pointing to the left, and this one is pointing to the right. And if you look at your molecule, when you add those electrons back in, you had 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have a lone pair to the left. I have a lone pair to the right. I have a total of 3 bonds between the 2 nitrogens. All right, so the picture you draw as a Lewis structure is the finalized MO picture that you get in the end. They are always the same. All right, y'all, much love, much love. If you haven't done discussion 39 yet, it is awful. It's just a lot. It's a ton of practice, and it's beautiful. And I need you to do it, but just don't be discouraged. It's graded on, did you try it? All right, y'all, much love. See you on Friday.